Glad you guys could make it back in this morning, and I hope you weren't up too late doing your homework that we didn't get to in the lab yesterday. But this morning we're very privileged to have a staff member from JPL, Kyle Edelberg, here to give a lecture on control systems theory. Kyle was here last year and gave just an amazing lecture. I'm sure you'll all be just completely engaged, not only with the content but with his style. Kyle he'll tell you in more detail about the experiences he's had, but you may, like I did at the end of the year last year, all of us may want to end up going to work for JPL as soon as we can at the earliest possible opportunities. I'll just turn it over to Kyle. Control systems for us in the race car are very critical to actually making the car move under positive control at all times and in a safe manner. The lessons that you'll get from Kyle today on control systems theory will give you an idea of what the concepts that you need to work with are, and then tomorrow we'll be back to give us a more practical lecture, taking advantage of the sensors and control systems that are physically on the race car, so that at the end of the week challenge, you'll actually be able to put everything that he's teaching you in these lectures into practice. Thanks.
All right, thank you, Ken, for the welcome back and for having me back. I'm really quite happy to be here for a couple reasons. One, I really like to be able to talk to you guys and share the experiences I've had thus far in robotics, and particularly in control systems and robotics. And the second is that, you know, if you guys choose to be, you are the next generation of robotics engineers, and I will be working with you at some point. It'll be you up here instead of me talking about control systems and robots. And so it's important to me to make sure that I pass down whatever thoughts, lessons learned I have had thus far to you. Like Ken said, I'm from NASA's Jet Propulsion Lab. We're a NASA center in Pasadena, California. It's a picture of it up here on the screen. We are NASA's flagship center for space robotics. So we do robotic exploration of the solar system. We also do a lot of terrestrial robotics as well, and earth science. I wanted to just kick things off with a quick video so you get a sense of the kind of things that we do. The sound's through my laptop, so I apologize for that, but. Okay, everybody's super happy because they worked for like 6 years on that project. So that is Mars Science Lab, also known as Curiosity. It's one of the rovers that we currently operate on the surface of Mars. That landing was in 2012. When that landing happened, I wasn't at JPL yet. I was actually getting my master's degree at UC Berkeley in mechanical engineering with a focus on control systems. And then I went to start to work at JPL in 2014, and I've been doing robotics there since. One of the reasons I like to show this video is one, because there's quite a lot in this in terms of what's going on technologically, but it also, it's an interesting story in that that system of how we landed Curiosity was brand new. This is the state of the art right now of how you land stuff on other planets. We can't do it any better than this currently. That idea was thought up by like a few guys at JPL. They got together and they thought about this problem of how are we going to land something on Mars, and they came up with this idea of sky crane, with this rocket system inverted with the rover lowering to the surface via a crane and a winch that connects it, and then it eventually flies away. The other reason I like to show that is because we're here today because we're talking about control systems. And one of the things that makes this system so unique is that it's fully autonomous. And so my question to you is, why is that system fully autonomous? Why couldn't someone on Earth just be joysticking this thing down to the surface? Yes?
Because light is too slow.
Because light is too slow. As fast as light is, it is not fast enough for a human to be able to do that. Because there's a 15-minute, depending on the way the planets are currently aligned, like a 15-minute round trip delay from Earth to Mars. So if you send a command, you wouldn't know if the robot received it until 15 minutes later. So that necessitates autonomy and necessitates control systems. So that's kind of why we're here today, is to talk about robotic systems that require, to a certain degree, either semi-autonomous or autonomous capabilities, and that they need control systems within them in order to achieve things like this. One of the things I want to mention, so like I said, this is my name. This is my email address at JPL, before I forget. Can everybody read this, by the way? Okay. Like I said, I'm here because I like to be here and I like to talk to you guys, but I'm also here because someday we may be working together, which would be really awesome. I want you to use me as a resource. If you have any questions, any comments, anything you want to ask about, you want to talk about JPL, you want to talk about not JPL, you want to talk about career paths in robotics, please feel free to email me. I guarantee you I will respond. I can't guarantee you when. It might take a couple days, but please, please email me. Email me 5 years from now. Say I took this course. I will remember that I was here, and I will remember who you are. Okay, so with that, I think you guys have done some like online training, right? You've done some stuff with control systems, is that right? Okay. Who wants to take a crack at saying what they think a control system is? Anybody? Okay. Please don't be shy. I know I'm big and I have shaved head and all that, but trust me, inside I'm a big softie. I'm really not gonna be harsh. Control systems basically get a system to do what you want it to do, in essence. I have a system, it's in some state. I want it to get it to some other state. How do I do that? I implement what's called a control system. In robotics, if you want to implement a semi-autonomous or autonomous capability, there's kind of 3 questions that the robot needs to be able to answer. And so I'm just going to write these down, and then we'll talk about them. And this is kind of my own take on robotics. This is my own philosophy. All right, the first is the robot needs to answer the question, where am I? The second, the robot needs to ask, where am I going? Or answer the question, where am I going? And then the last question is, how do I get there? Okay, what am I talking about? Well, we can think about this in the most literal sense. That suppose I have a mobile robot and it's right in front of me and I wanted to get over to that door. So the robot needs to be able to answer the question, if I wanted to do something, if I wanted to move somewhere, it needs to first know, well, where is it right now? Then it needs to be able to answer the question, where am I going? You're going to the door. And then it needs to figure out, how am I going to get to the door? This first question of where am I is answered by the field of study called state estimation, which is something I'm not going to teach, but you will learn about next week. So this is state estimation. Second question of where am I going? This is what we call a planning problem. You have an objective. How are you going to achieve the objective? You need to figure out how to get from point A to point B. So this would be planning. Once you have a plan, it's like, how do I execute that plan? This is control systems. So you get there with controllers. So I gave the example of the literal interpretation of what I'm talking about here, which is the robot driving over the door. But you can also look at this in a more abstract sense, because this works for applications well beyond just mobility. You could also look at, like, I want to control the temperature of this room. And you can take where am I, not to mean so much where's the room, but what is the temperature of the room right now, is the question you need to be able to answer in order to know how to get to the desired temperature, which is where am I going. And then how do I get there would be whatever controller lives in the HVAC system, which takes you from 60 degrees to 70 degrees. Does that concept make sense? OK. So this is kind of where control systems fit in. It's how you actually get the system to do what you want it to do. I start with that because I want to make sure it's clear where controls fit in before we just jump into, like, what is the controller doing and what are the different types of controllers. I want to make sure that the big picture makes sense. The other reason I point this out is because controls is like a whole field of study on its own. It existed before, well, debatable, but it existed before robotics, basically. So what we're looking at, though, is controls within robotics. So I want to frame it in this context. And just to keep in mind, as we go through control systems today, controls are very mathematically intense. Like, proper control theory is very mathematically intense. It requires calculus, linear algebra, differential equations, a whole bunch of courses that you would take in college. Like, you wouldn't, if you were to study, say, mechanical engineering like I did, and you want to take a control systems course, you wouldn't be able to take it typically until your junior year of college. You would maybe have time to take one more control systems course. But any university with a controls program will have like a dozen different control systems courses at least. And you can get an entire PhD, not just in control systems, but you can get a PhD in one little slice of controls. So I just want to say that because we have 2 hours together. And so I want to make sure that you guys understand that there's a lot of information out there. There's a whole bunch of stuff. And what I'm going to try to do is really help, if I can, frame the context of why controls is important, help you implement the controls you need on your vehicles, which we'll talk about more about the practical implementation, like Ken said, tomorrow, and answer any questions that you may have so that the context of controls and some of the terminology makes sense. Sound good? OK. So we talked about the motivation of controls and how sometimes we need control systems because a human can't do it, like here in this case. Humans were just sitting here waiting for this thing to execute. And we couldn't have done it ourselves because of the round-trip delay. There are also cases where you could have a human do it, but you prefer to have a controller do it. A good example would be like cruise control in a car. Like, I'm totally capable of maintaining 70 miles an hour on the highway, but I can also turn on a control system in my vehicle, which looks at my current speed, and it looks at what speed I'm trying to get to, and then it uses the throttle to the engine as a way of maintaining that speed. So that's an example of a control system. So more formal definition here of a controller is that a controller, it gets something called your system state to a desired output or desired value based on manipulation of an input. So to explain that a bit more clearly, I'm going to draw a couple diagrams here. And I'm going to borrow nomenclature and diagrams from control theory so that if you guys go Google stuff or whatever, this will look somewhat familiar. So suppose I have a system I want to control. Back to the cruise control example. It's a car, and I'm trying to maintain a speed in the vehicle. In control systems, that thing you're trying to control is called a plant. Now, the reason it's called a plant dates back to the origins of control theory, which gets into like chemical engineering processes, where they were trying to control chemical processes, and so what they were controlling was a plant. So don't think too much into the term itself. It's historical, and it doesn't necessarily make sense anymore, but that's what they're called. So the plant, like in this case, would be my vehicle, and I'm trying to maintain its speed. I have some inputs to my plant. Right, in the case of cruise control, what's my input? Well, that's a good point, actually. Speed is an input, but in that sense, speed is what I want the output of my plant to be, right? What am I using to control the speed? The throttle. Yeah, the throttle. So in our example, this would be throttle. In control theory, this is typically given the label U. U is a variable that's just commonly referred to as the input to your plant. Okay, so the output of my plant, like we just said, is my speed. This is the thing that I care about. This is typically assigned the variable y. So in its simplest form, what a control system does is it manipulates u in order to achieve some desired value for y. And that's really it. All the PhDs and controls in the world and all the different theories that are out there are using this to achieve that, the desired value of that. And that's really what it boils down to. Good so far? Cool. Okay. There's two pretty discrete classes of controls. One is called open-loop control, and the other is called closed-loop. And we're going to talk about what these mean. Whether or not you're open or closed refers to whether or not you are using knowledge of this output to affect this input. Let me explain what I mean by that. What I've drawn here is actually an open-loop controller, in the sense that I'm blindly manipulating my input in order to achieve my output. I'm not actually measuring my output. So example of this would be, suppose I would not recommend this, but suppose I was driving down the highway and I wanted to maintain 70 miles an hour and I closed my eyes. And now I'm just manipulating the throttle and trying to stay at 70 miles an hour. Do you think I could do it? No, maybe? Yes? Who said yes?
Yes,
on a flat road. Why on a flat road?
Because you could find the throttle position such that the air resistance is equal to the engine power.
That's exactly right. So if I were on flat ground, I could probably do this assuming there were no turns and no police. But I still wouldn't recommend it, not in that particular case. However, your colleague's point is that if you can think about it like, suppose I'm on a flat ground, the road is perfectly smooth, the wind is fixed at 0 miles an hour, and I'm driving at 70 and I'm looking at the speedometer. Now I close my eyes. What am I going to do? I'm just going to keep my foot exactly fixed where it was, right? If nothing external in my environment changes, I should just stay at 70 miles an hour, right? That's kind of the essence of open loop control. What we're doing there in that first step where I'm driving along with my eyes open, looking at speedometer, is something called calibration. I'm learning what throttle angle gets me 70 miles an hour for this given set of fixed conditions. And then I don't need the speedometer anymore. Until what? Yes?
The conditions change.
Until the conditions change, right. I hit a hill. Start to go up an incline, what happens? A car starts to slow down. Why? Because force of gravity is causing a force on the vehicle, right, which is going to cause me to slow down. I'm trying to increase my potential energy, but I have a fixed throttle angle. So what if I opened my eyes again and I looked at the speedometer and I saw that now I'm going 65? What am I going to do? I open my eyes. So now what have I done? I've taken a what? It depends on how you look at it. If I'm doing this live, I would call that I've taken a measurement. So there's kind of two ways you could do this. I could say, I'm going to figure out what throttle angle works for every angle of hill ever to keep me at 70 miles an hour. And then I'm going to put that in a big lookup table, and I'm going to load it into my brain, or I'm going to load it into the car's brain. And then I'm never going to look at speed again. That would be open loop calibration through and through. In this particular case, though, what I'm getting at is the idea that while I'm driving, I'm going to take another measurement, and I'm going to use that measurement to what? Change my throttle angle, right? That is closed loop control. So opposed to the initial step where I would call that an experiment, where I figured out what throttle angle got me 70 at flat ground, and then I never opened my eyes again. I just always stayed there, would be open loop control. If I ever want to go 70, I'm just going to apply that throttle angle. Now in this case, I'm saying while I'm driving, I'm going to open my eyes periodically, and I'm going to look at what the speed is. And then I'm going to adjust the throttle based on what I'm seeing. That's the distinction between open loop and closed loop. So in the case of closed loop, what I'm actually doing, and this is why it's called closed loop, is I'm taking that measurement and I'm feeding it back. And I'm going to leave this disconnected for right now. And I'll talk about why in a second. But I'm going to feed it into my controller. Now, in the cruise control example, I'm trying to get to 70 miles an hour, right? That's something called my set point or my reference. That's what I want my controller to achieve, the output of my plant to be. That typically has the variable R for reference. So again, this R, 70 miles an hour in our example. But actually, I think the speed limit in this state is usually 65. I'm from Southern California, it's 70. So I don't want you to think that I drive around breaking the law or that I drive around with my eyes closed. This is just an example. All right, so reference comes in. And then something magical happens. What do? I put a summation block here, and I subtract away my current speed from my desired speed. And this gives me something called an error signal, and I feed that into my controller. This is given the variable E in controls. And we've just completed the loop. So back to my example, I'm driving my car, I am at a certain throttle angle, I get a certain speed, I open my eyes, I take a measurement, I say, oh, I'm at 65, I want to be at 70. I'm off by 5 miles an hour. I'm going to do something. My mind and body are going to do something to change this input so that I can get this to 70 miles an hour. Are there any questions on this? Okay, out of these two, which do you think is more complicated to implement? Closed loop, yeah. Which one do you get a PhD in? Closed loop. You can do this in like very fast. This is much more complex and more difficult to analyze. Why? Because you introduce feedback. That means that now, when my plant changes and this output changes, that goes all the way back here through my controller, and it's going to change my input. And that has all kinds of interesting implications. And that's the heart of what you would study if you were to study control systems. Okay, would you ever use open loop control? Yeah. Why would you use open, oh, yeah.
So when you just have like input and output, would that be an open loop? But then when you put like, and then when you like have the controller and then you have closed loop?
Yes, that's right. And thank you for pointing that out. I should have drawn that distinction. What your colleague's saying is when I didn't have any of this and I didn't have the feedback path, just this part is the open loop controller. When I draw this connection, it's a closed loop controller. There's one more thing about that, though, is that in reality, and you know what, just to make this super clear, let's call this closed loop. There's still a controller in open loop control. So actually what I said is slightly incorrect. The reality of what open loop control looks like is I have some reference which comes in, and it still goes into a controller. That feeds into my plant, and I get some output. All right, so this is open loop. Okay. So reference comes in, again, me driving, eyes closed, I want to go 70. Goes into some controller. In this case, my controller is apply this throttle angle when you want to go 70. So I apply that angle, and I'm going to get some output. And it doesn't matter what my output actually is. That's the key distinction between open and closed, is I could be going 0 miles an hour. I'm not going to change my input because I have no knowledge of that. Okay, so would we ever use this? In reality, yes. Why?
Because there might be some cases in which case I do not have a good sensor
Yes.
to measure my output.
Absolutely. There are cases when you don't have a sensor to measure your output. And in fact, that ends up being the case a lot of time. And you can take two approaches to that. One is to say, OK, I can't measure it. I'm going to do open loop control. And maybe that's sufficient for your application. Another is to say, OK, I can't measure what I really care about, but I can measure something else similar. Like maybe I can't measure the temperature of the combustion chamber, but I can measure the temperature of the wall around it. And I can infer from that what the temperature of combustion is. And then I can control it. That's back into the first question of where am I? That's the state estimation problem. And so I don't want to talk too much about that one, particularly because you guys will learn more about it next week. But yes, there are cases where you can't measure your output. There are other cases, too, where this just isn't necessary, where an open loop controller is completely fine. If I have an application where all I'm ever doing is driving around on flat ground, there are literally no changes to my environment, then I can just go ahead and implement this, and it'll work fine. But when we talk about controls, when people say controls, it's almost implied that they're talking about closed loop. Because the reality is conditions change all the time. Nothing is perfect and nothing is always static. And so you need a controller to compensate. Right, suppose back to my, 1 second, then I'll answer your question, or get to your question. Back to my example of driving on flat ground. As I'm driving, what's happening to the gas in my tank? It's going down, right? So actually, what's the car going to do if that's the only change? Eventually, it will stop. Yes, it's a very good point, and then I'll be at 0 miles an hour. But as I burn the fuel, what's happening to the weight of the vehicle? Decreasing. So what's happening to the rolling resistance, the drag on the tires on the ground? It's decreasing. So what's the car going to do? It's going to speed up. Do I know that in open loop? Nope. I don't. OK, there was a question or a comment.
So, judging by the complexity of the closed loop versus the open loop, I make an assumption that open loop is obviously cheaper than closed loop.
That is a very interesting point because it gets into how do you actually implement these things. It's cheaper in the sense that for closed loop, what I'm not drawing here is to measure this, is to get this output, I have to measure it, right? So I need to buy a sensor. Now, a sensor could be extremely cheap. It could be 50 cents, or it could be hundreds of thousands of dollars, depending on the application. So yes, this has the potential to be quite expensive. However, this gets into an interesting question of how are controllers implemented? How do you guys think we implement these? If I wanted to take that knowledge in my brain of if I'm going 65, I need to do something with the throttle in order to get to 70, how would I implement that in a robot? Yes? Yes, by using computer and code is by far the most prevalent way in which we implement controls. Controls actually dates back, though, so far that you can find examples of mechanical control systems, mechanical closed-loop control systems, and electrical closed-loop control systems. Can you think this is like a tangent, but why would you want to implement a controller electrically as opposed to in software? Like, suppose I could make a circuit which exactly replicates what I can do in software. Why would I do that as opposed to implementing in software? Yes?
In case the code doesn't work, or like if it's less points of failure.
Less points of failure, yes, it could be.
Could be slightly faster.
Yes, exactly. Actually, it could be significantly faster than a computer can execute the code. To get faster and faster on a computer, you have to pay more what? Money, right? So you can implement actually something dirt cheap in analog circuitry. Yes?
Don't have to pay the power cost of running all the other systems on the computer?
Yes, very good point. And a huge driver in robotics right now is power. Power is like the name of the game. Power and decreasing power consumption and increasing power storage are big, big deals right now in robotics because mobile systems consume a lot of power and we don't have the battery technology to support, like, say I have a humanoid robot, I want it to run 8 hours, forget it. It's not going to happen. It's not possible right now. Not a full-scale one anyways. 2 hours max. That's where we're at right now. So power consumption is a big deal. Okay. So are there any lingering questions on the distinction between open and closed-loop control before we start to dive into closed-loop control? Yes?
So for example, if you're driving on a straight flat road and there's no potholes or anything, that would be considered an open loop because you know your environment and then you know that nothing is an obstacle in your way.
Good question. You could actually do that either with an open loop controller or a closed loop controller.
What would be the difference between the two?
Sure. So in the open loop case, driving on flat ground, I'm not going to look at what my speed is. It's as if my speedometer has been covered up. And I'm going to try to control my speed regardless. Now, in your example of flat ground, no potholes, whatever, I can probably do a pretty good job. This will also do a good job. This will take my output and run it through a controller compared to a reference and compute some throttle angle. Now, in the case of 70 miles an hour on flat ground, it's going to say I'm already going 70 miles an hour, so it's not going to change my input to the system. So both open and closed loop control will work in that case. And it would be a decision as the engineer as to what one you want to implement. However, as soon as you hit a hill, this one isn't going to work very well anymore, and that's where you would want this one. So this will work in both cases. This would only work in that specific case. Does that make sense?
Yes,
Oh, okay, cool. Yes?
If you have a sensor that determines your environment and would like measure the angle of the hill and then adjust the power based on the angle of the hill, is that open or closed?
That's a very, very good question. I would still consider that open loop. So does everyone understand the question your colleague asked? He's asking, what if instead of measuring my speed, I'm measuring something else, which is I'm measuring the angle of the hill. And based on the angle of the hill, I'm changing what my input is. Is that closed loop or open loop control? That is why it's still open loop control. It's because it's not another way of feedback. And here's the thing about that, is if I affect my input in that case, am I going to change the slope of the hill? Nope. All it is in the open loop case, suppose I have knowledge of the hill angle, I can put that in here. So I can have multiple inputs to my open loop controller. I can say I want to go 70, I'm on a 5-degree slope, I'm going to apply this input. Okay. All right, so let's talk a bit about closed loop control. All right, so I'm just going to redraw that very quickly. But this time I'm going to make a little bit of a distinction. I'm going to draw another box. Okay. Cruise control. Car's going 70 miles an hour. How do I know the car's going 70 miles an hour when I open my eyes? Speedometer. So there's a sensor, right? Does that sensor output, like, imagine what is that sensor? Really, that sensor is either measuring wheel speed or it's measuring the engine speed, one or the other. If it's engine speed, then it's looking at what gear you're in and it knows your tire size, and then it can tell you what speed you're going. What do you think the actual output of that physical sensor is, though? Is it miles per hour speed? Yeah, ticks per second or voltage or something, right? So when I slap that sensor on this system, am I really measuring my speed? No, I'm measuring something else. And then I'm taking that information and I'm turning it into a speed. That's the estimation problem. So my sensor, even if all I'm doing is saying 5 volts equals 70 miles an hour, 2.5 volts equals 35 miles an hour. That's still some sort of estimation going on in order to get to what I actually care about here, which is my speed as compared to my reference. Right? I don't care about controlling voltage on that sensor. I care about controlling my plant output. I'm just measuring with the sensor the outputs of voltage. Here's the other thing about sensors. Are sensors perfect? No, they are not. Will sensors ever be perfect? Nope, they will not. You can pay a lot of money to get a really good sensor, and you can get it more and more accurate the more money you throw at the problem. But is that a viable solution for a lot of applications? No. Why? Because a lot of stuff we work on ends up getting mass-produced. Like the inertial measurement unit in your iPhone. I mean, think about how many iPhones there are. This thing measures acceleration as you move it around. And has a magnetometer in it. That's why you're able to use it as a compass. But Apple can't buy a $100,000 military-grade IMU and put it inside your phone. First of all, it wouldn't fit. They're huge. But second of all, the company would go bankrupt, right? No one would buy that. It's ridiculous. So instead, what do? They put a cheap sensor in there, and they hire a bunch of people like you guys to come up with really clever estimation algorithms in order to estimate, based on an imperfect sensor, far from perfect sensor, what the actual acceleration of your iPhone is as you wave it around doing Snapchat or whatever it is you guys do. Okay, so again, estimation. That's something you'll learn about later, but I throw it in here because there is no decoupling controls from estimation at the end of the day. When you go to implement this, even if you're just taking that sensor output, like I said, applying some gain to it, you're still doing estimation, and it's still important to remember that you can never physically measure your output perfectly. You always have some sort of error. You always have some sort of estimation you have to do. Does that make sense? Okay. So let's talk about the world's simplest controller that's closed loop. This is called Bangbang Control. And I love this name because it's such a great description of what this thing is. Okay, let's go back to the cruise control example. Suppose I'm driving with my eyes open. So we're in closed loop mode. I'm looking at my speedometer. My speedometer is talking to some sensor, right? It's doing some estimation. It's telling me, hey, you're going 65 miles an hour. Like we talked about before, as a human, if I want to go 70, I'm going to put my foot on the gas more, right? How much more? Yes?
Enough until you get to that speed.
Enough till you get to that speed, right? Do you think if we took, how many of you are 40 cars, and we put sensor on the throttle and we ran that experiment, that you would all press it the same way? No, probably not. It'd probably be similar though. How many of you would just hit the gas full until you hit 70? No one will admit that, right? You could though, right? Conceivably, you could just say, I'm gonna romp the throttle all the way down. That's the fastest way to get to 70, right? So in some sense, it's like, why don't we do that? Okay, I hit 70, now what? You have to take your foot off, right? Otherwise, you're definitely gonna get pulled over. That is bang-bang control. Bang-bang control is, if I'm below my target, apply this input, fixed. If I'm above my target, apply this other input. So in the cruise control example, it would be, if I'm below my speed, press the gas all the way to the floor, regardless of how far off I am, even if I'm at 69.5 miles an hour, full throttle. As soon as I cross some value, say 70, no gas. What's going to happen? Yes?
Undulate violently like that. I mean, it fluctuate violently.
It would fluctuate violently, and why is that the case?
Because you're accelerating a much unnecessary. You're accelerating unnecessarily when you pass or very close to the line. So there's no sense of like getting more accuracy or finer correction.
Right. There's no sense of, I should probably let my foot off the gas a little bit as I approach my goal, right? So what's going to happen? I'm going to overshoot 70. And then what happens when I take my foot off the gas? Undershoot meaning what? The car's going to what? It's going to slow down, right? Then I'm going to go below 70. What am I going to do? Gas. Off, gas, off, gas, off, bang, bang control. Dirt simple. So if I were to implement this in pseudocode, it's literally like 4 lines. If, again, what's that value? I'm trying to control the speed, right? But I have a target, 70. What's the difference between those two values? Error. What's the variable? E. So I can have an if statement. If E is less than, I'm just going to say 0 in this case. But in reality, it could be a little bit more complicated if you wanted. Then my input to my plant, which is what variable? U. And again, this isn't because you have to pick these variables. It's just if you go look at literature, you're going to see these terms all over the place, or this particular nomenclature. I just want it to be familiar to you. Then U equals, let's say, value 1. Else, U equals value 2. If I'm below 70, full gas. Otherwise, I must be at 70 or above it. Value 2, no gas. 4 lines. It's like 30 seconds. And you have a closed-loop controller. Would I ever use bang-bang control? Yes. Like open-loop control, it sounds like a little ridiculous, right? Why would I do that? But there are actually applications where this makes a lot of sense. In the case of throttle, I can apply a little bit. I can apply like middle amount. I have all kinds of options, right? How much throttle I want to apply. When we talk about inputs, is that always the case, that I have infinite resolution over how much I'm applying? What?
That's not always the case.
Not always the case, right. Suppose I have an older HVAC system, and I'm trying to control the temperature of a room. The reality is the AC compressor that's cooling the thing can either be on or it can be off. There is no in-between. And so in the end, you have a thermostat which is doing bang control. It's saying if the temperature of my room is too low, then shut the AC off. I don't need it. But once the temperature rises above some value, kick it back on. That is bang. Now, in the case of your car, as your colleague was pointing out, bang control will probably feel pretty violent. But in the case of a room, it works really well. Why is that? Because the effective rate on the output of your system is relatively low when you're talking about AC. You kick on the AC, it kind of takes a while. It's like this slow system, cool down the whole room. So you don't get this sharp change in output. In the case of your car, particularly if you have a nice one, not me, I drive a truck, if you hit the gas, you would feel the acceleration immediately. Your speed would start to change very rapidly. So in that particular case, if you're worried about the comfort of the human passengers, you may be more interested in something smoother. Does that concept make sense? Okay. So that's bang control, but I just kind of set up motivation for the next kind of controller we're going to talk about. Before we do that, are there any lingering questions on bang, open, closed loop? Okay. Then let's talk about something called PID control. Just by a show of hands, how many people have heard of this concept before? Okay. Who knows what the letters stand for? Yes.
Proportional integral derivative.
Yes, proportional integral derivative control. Who's implemented one of these on a real system? By another show of hands. Okay. How did it work? Someone want to tell me what your system was? Did it work or did it not? Yeah.
It was a wall follower, so it judged distance from the wall and used the PID.
Okay, that's like what you guys are doing in your class, so. Yes.
FLO
But that's
true, reading from the Lego gyroscope and you could work with
Okay. Anybody else want to share a PID experience? Yes.
You just have a robot and you want it to drive straight using a gyroscope.
Okay. Last one? Oh, you guys on the same team.
It was just a drone that could stay level.
Okay. Last one?
So I'm on a first robotics team, so we PIDs that use encoders on the wheels.
Yep. Okay. Okay. So a handful of you have already implemented something like this. What was the hardest part about implementing PID control? Was it writing the code? Was it working with the electronics? Was it tuning it? What was it? Yes. Tuning it. Anybody else have the same experience? Tuning it. Yes. Okay. Here's the thing about PID control before we launch into what it is. This is by far the most widely used control system in all closed-loop applications. By far. You know, I said you can get PhDs in like specific types of controllers, right? Not this one. This has been studied to death. And it's very simple. The problem with PID control, and the reason it's not interesting from an academic standpoint, is that this controller consists of 3 gains, and we're going to talk about what those are. There are these 3 magical knobs, and when you change these values, things either work or they don't work. And from a certain standpoint, you just don't know what's going to happen when you fire this thing up the first time. That's the problem with PID control. The reason it's used so much is because most of the time this thing works. You can get it to work. You'll find a set of gains where this thing's going to work beautifully. And then there's all kinds of hacks and all this stuff you can do with PID control if a normal, regular PID controller doesn't work. You could play all these games to get this thing to work. But at the end of the day, it's dirt simple, which is a plus. It's dirt simple, which is a con. Like, as much as I love PID control, I also hate it. And I've implemented a lot. So let's talk about what it is. So I'm going to write the control law down, and then we'll talk about it. So remember, U is my system input, right? If I want to implement a PID controller, my input equals some value called times called KP times E, which is what? Error, plus something called KI times the integral, and I believe that some of you have not had calculus yet. So we're going to do our best to avoid what this weird symbol means in terms of hardcore calculus, but I'll talk about it. So KI times this is integral of my error plus KD, and then here comes another calculus term times the rate of change of my error. This dE dt just means how quickly is my error changing. Okay, that's PID control. You can implement this in like 4 lines of code too. Is anyone going to pay you to write this in code? As an engineer? No. What do they pay you to do? Find these magical numbers. That's what you get paid for. So these are the 3 knobs of PID control. Now, there is some really beautiful math behind PID control that can explain why on certain systems this thing works so well. It's beyond the scope of this course. Your first controls course, if you choose to take one in college, which I recommend it, I think controls is a lot of fun. Because controls, there's the math and the theory, and that's all well and great, but what's really good about controls is to implement a controller, truly implement one, you need to understand your whole system. Because typically you're writing it in code, that computer's gonna talk to electronics, which measure things, which you also need to understand, and you need to understand this plant that you're controlling. So it's like electrical, software, mechanical. You need to understand all 3 to really implement stuff like this, which personally I love. So if you're interested in that kind of thing, that's my pitch for controls, basically. Okay. So 3 values that are the essence of what makes PID work and what makes it so difficult. So let's talk about these real quick. The simplest one and the most widely used is KP, this proportional part. So this guy here is the P part of PID. Let's just ignore this for now. Okay, let's just talk about this term. Back to my cruise control example. Bang, bang, the problem was, if I'm at 69.5 miles an hour, my foot is still fully on the gas, right? Now imagine, though, that instead of just saying I'm going to go full gas, I have a proportional controller, meaning I'm going to apply some gain, some fixed value multiplied by my error. That's going to be my input. So as I approach my target, like say I'm going from 60 to 70 miles an hour, what is my foot going to do on the throttle as my speed increases and E starts to go down? Yeah, it's going to lift up a little bit. It's going to lift up in proportion to this value. So this is how you get smoothness in approaching your target. It's one way anyways. What it means is the further I am away from my goal, the more I'm going to apply to try to get there. And as I start to get there, I'm going to apply less and less and less and less and less, so that if everything works out perfectly, I'll just, boop, barely hit my value, without any of this back and forth stuff that you would get with the Bangbang controller. And in fact, we can plot that. Okay, so if I have time, 2 different plots, time on my x-axis, and I'm plotting error. And the other thing I'm plotting is U, my control input. So we're going to look at, as my error changes, what's happening to U, or vice versa. Suppose my error starts here at 10 miles an hour. My U is going to be KP times 10. What's KP? Who knows, right? That's the trick, is you got to pick this value. And it's totally different for every application. Why? Because we're talking about speed turning into a throttle angle. is that the same as temperature control of a room, like degrees to like AC power? No. So it's totally application specific. Anyways, let's just say KP is something. The point is the trends will be the same. So if my error is 10 miles an hour, my U is going to be some fixed value. Now suppose this is enough so that my car is speeding up. What happens to error? It decreases. As it goes down, what happens to U? Decreases. Now eventually what we want is error to get to 0, right? Here's a kind of funny thing that happens though. What is my throttle angle if my error is 0 with just a proportional controller? Well, what happens at 0 throttle? The car slows down. What's up with that? Will my error ever actually get, well, let me look at it this way. Yeah, will my error ever actually get to 0 then? If as I approach my target, I start to take my foot off the throttle? No. No, because this is the problem with the proportional controller. It always leaves you with something called steady state error. The reason is you have disturbances, which is the term in controls, meaning external things acting on your plant that are not you. These are called D for disturbance. Disturbance would be air resistance, rolling resistance, mechanical drag, all kinds of things which mean that when I apply 0, my car slows down. Proportional controller can't overcome that. It just can't. So what happens is your error doesn't go to 0. Your error starts to go down, and so does your throttle. When that happens, your car starts to slow down. So your error starts to go up a little bit. So your throttle picks back up, and you end up hitting what's called a steady state. And steady state in controls means after all the initial conditions are no longer in effect. Doesn't matter what I started at. I let this thing run for enough time that I've gotten to a fixed state of operation. That's steady state. You'll always have some error here. Is that a problem? It might be. It depends on the application. I can tell you lots of applications that use proportional only control because at the end of the day, they don't need this to be perfect. And that's what makes controls so tricky. When you're actually in the field implementing this stuff on robots, is like, where do you stop? How good do we need this? Well, you could say, well, let's just make this as good as possible. Well, but then you're spending all your time in your controller, and you're missing the other 2 questions that I was talking about. Sometimes you can't get this to 0. It's just not possible. But there are things you can do which help. And that's where this guy comes in particular, with this problem. And we've only got a few minutes left, so I'm going to just mention what this is briefly. We'll start tomorrow by recapping what PID control is, and then we're going to talk about how you would implement this or the Bangbang controller on your vehicles. Sound good? OK. This here's an integrator. How many people know what an integrator is? Just so I've got some idea. OK, so certainly not the bulk of you. Again, this is a calculus term. So it's a little unfair that I'm springing it on you. But unfortunately, we can't talk about PID control without mentioning this. An integrator, think of it as a summation. What an integrator does is it says, in this context, is it says, OK, what is my error right now? OK, it's 5 miles an hour. I'm going to remember that value. Next time my controller updates, and in software this happens at some fixed rate, I'm going to add that old error to my new error. The next time it updates again, I'm going to add it again. And I'm going to keep summing my error over time. What this is doing is it's looking back in time. The effect of this is it can drive this steady state error down to 0. Because what happens is proportional control just says, oh, I have some error, apply this value. It's very reactive. It has no memory. This guy has a memory. It remembers that, hey, last time we had this error. And last time we had that error. And last time we had that error. And these are adding up and they're not adding up to 0. And every time it adds, it gets bigger and bigger and bigger and bigger. So what happens to you if I have this kind of term involved in my controller for a given fixed amount of error? What does this term do? It gets bigger. That's why it gets rid of steady state error. So if we just plot this ki term, like the effect of this, if this is my error, if my error is fixed, my proportional term would just be fixed too. But my integral error is going to look like this. Or sorry, my integral term. Okay? When you're doing this summation, you're adding this guy with this guy. And the conjunction of the two, with these powers combined, you can have the smoothness of backing off before you hit your target, while also having this integrator which causes you to drive your steady state error to 0. Okay, I know there's a lot of concepts. Are there questions? Yes?
Are there some systems that only use the first part, just the P?
Yes. I have friends at Berkeley. They work on robotic exoskeletons for paraplegics. And the first version, at least, was driven, like those things work by following a joint trajectory to help people walk. Proportional only, because it worked. You had a question? Let me go back to you. Yes?
So how do you get the integral to not try and overshoot the steady state?
We will talk about that tomorrow. Yes. That was the last question?
And so, is there like some mathematical way to find the K value to just keep on testing?
There are different approaches to finding these. There are 3, and I'll mention them all very quickly right now, and then tomorrow we'll talk about them. One is by guessing. And you can make an educated guess or an uneducated guess. The very first time you do this, it'll be relatively uneducated. But then you get better at it. The second is something called Ziegler-Nichols tuning. It's an approach developed in like the 60s or something. These guys came up with an algorithm for how to find these experimentally. The final is something called model-based design, where, and this is something we'll chat about tomorrow, you can imagine that I could probably come up with a mathematical model that describes the physics of the car I was talking about, right? Driving on ground, flat ground, I'm trying to control the speed of it. Right, I could have like a model for my engine, a model for the tires, aerodynamics. I can use that model to inform what these values should be. And it's actually very cool because I can prescribe what I want my response to be, and out pops these terms. And there are lots of techniques for doing that. Okay, we're out of time. I'll be around to help you guys with your lab and answer any questions you might have. Again, feel free to email me anytime, and I'll be back tomorrow to talk about the more practical implementation side of this. Okay, thank you.
Kyle's going to be back tomorrow, so we'll give him a t-shirt tomorrow.
Okay, thanks, guys.
Unless you want to. Perfect.
I'll take the one.
Awesome. So what we're going to do starting now is maybe take a quick break. If anybody needs to go to the restroom, you can do that now. And we'll get set up to jump back into the Ross lecture and lab and check in where everybody got to yesterday and last night. And the plan after that is we'll be in here for the special invited seminar, go break for lunch, and then we'll transition to our normal classroom and lab work area. And Kyle will probably be around roaming and available to answer questions about some of the work that we're going to do today with the safety controller and laser scanner in particular.